Welcome back, curious minds and AI innovators. Today, we're diving into one of the most exciting frontiers in artificial intelligence, self-supervised learning. Imagine a world where AI can learn from oceans of unlabeled data, just as humans learn by observing the world around them. No more relying solely on expensive, time-consuming human labeling. Instead, AI can teach itself, unlocking new possibilities for learning and understanding. In this video, we'll explore how self-supervised learning works, why it's revolutionary, and what it means for the future of AI. Let's embark on this journey to discover how AI can learn more like us through experience and observation. Traditional AI has always depended on massive amounts of labeled data images tagged by humans, text annotated by experts. This process is not only expensive and time-consuming, but also doesn't scale well. Meanwhile, we're surrounded by an endless supply of unlabeled data, billions of images, trillions of web pages, and countless hours of video content. Self-supervised learning offers a solution by allowing AI to generate its own learning signals from this raw data. It's like giving AI the ability to learn from experience, just as humans do, opening up a treasure trove of opportunities for smarter, more adaptable systems. Self-supervised learning, or SSL, is a paradigm where AI systems generate their own supervision from unlabeled data, without needing human-provided labels. The core idea is to create artificial tasks called pretext tasks directly from the data. By solving these tasks, the AI learns general representations that can be transferred to real-world problems. Think of it like a child learning language by listening to conversations and figuring out patterns, rather than being explicitly taught every word. The ultimate goal is to develop AI that captures the underlying structure of data, enabling it to adapt and perform a wide range of tasks. Self-supervised learning operates in two main phases. First is pre-training, where the AI creates artificial tasks from unlabeled data like predicting missing parts or reorganizing shuffled elements. By solving these, the model learns rich, transferable representations. No human labels are needed at this stage. The second phase is fine-tuning, where these learned representations are adapted to actual downstream tasks, often requiring only minimal labeled data. This strategy allows the model to understand fundamental patterns and structures, making it highly adaptable and efficient when tackling real-world problems. The magic of self-supervised learning lies in its pretext tasks. By challenging the model to predict missing information or reorganize data, it's forced to understand the underlying structure and relationships within the data. This deep comprehension is what allows the model to transfer its knowledge so effectively to real-world tasks. The process mimics how humans learn from context and experience, building a foundation of understanding that can be applied flexibly across different domains and challenges. In the world of images, self-supervised learning employs creative pretext tasks. For example, the model might be asked to predict how much an image has been rotated, reassemble shuffled image patches like a jigsaw puzzle, or predict the color in grayscale images. Other tasks include predicting the relative positions of image patches. These challenges force the AI to develop a deep understanding of visual structure, context, and relationships, which are crucial for tasks like image recognition and object detection. For text, self-supervised learning shines through tasks like masked language modeling, where the AI predicts missing words in sentences, as seen in models like BERT. Other tasks include next sentence prediction, determining if one sentence logically follows another, and sentence ordering, where shuffled sentences are put back in the correct sequence. These tasks help the model grasp grammar, context, and meaning, enabling it to excel in applications like translation, summarization, and question answering. Self-supervised learning extends to video and audio as well. For video, tasks include arranging frames in the correct sequence, predicting if a video is sped up or slowed down, or forecasting future frames. In audio, the model might predict future segments, match sounds with visual sources, or fill in missing audio. These tasks enable AI to understand temporal dynamics and relationships, which are essential for applications like speech recognition, music recommendation, and event detection. Self-supervised learning is revolutionary because it leverages massive amounts of unlabeled data, reducing the need for costly human labeling. It allows AI to make use of data that was previously considered useless, scaling effortlessly to internet-sized datasets. The representations learned are more robust and general, capturing the true structure of the data and leading to better performance on new tasks. By mimicking human-like learning, SSL builds common-sense understanding and foundational knowledge, pushing the boundaries of what AI can achieve. One of the biggest advantages of self-supervised learning is its data efficiency. By tapping into vast pools of unlabeled data, SSL reduces the reliance on expensive, manually labeled datasets. This makes it possible to train models on a scale previously unimaginable, using data from across the internet. As a result, AI systems become more adaptable and capable, ready to tackle a wider range of challenges with less human intervention. Self-supervised learning enables AI to learn more robust and general features from data. These representations capture the underlying structure, making models less prone to overfitting and better at generalizing to new tasks. This means that AI trained with SSL can adapt more easily to unfamiliar situations, perform well with less data, and deliver state-of-the-art results across a variety of domains. A key strength of self-supervised learning is its ability to mimic how humans learn from observation. By learning from context and relationships within the data, SSL builds a kind of common-sense understanding. This foundational knowledge allows AI to approach problems more flexibly and creatively, just as people do when faced with new situations. It's a step closer to truly intelligent machines. Self-supervised learning has led to state-of-the-art results in many domains. Models trained with SSL often outperform those trained with traditional supervised methods, especially when labeled data is scarce. SSL enables more sample-efficient fine-tuning, better few-shot and zero-shot learning, and robust performance across diverse tasks. This makes it a powerful tool for advancing AI capabilities. How does self-supervised learning compare to other learning paradigms? Unlike supervised learning, which depends on human-labeled data, SSL learns directly from unlabeled data by creating its own learning signals. This independence from external labels makes SSL more scalable and adaptable, especially when labeled data is limited or unavailable. Compared to unsupervised learning, which often lacks clear optimization goals and focuses on clustering or density estimation, self-supervised learning offers more structure. SSL defines specific pretext tasks, giving the model clear objectives and making the learning process more effective. This structured approach leads to better representations and more practical results. Semi-supervised learning uses a mix of labeled and unlabeled data, while self-supervised learning relies solely on unlabeled data for pre-training. SSL is especially powerful when massive, unlabeled datasets are available, making it ideal for scaling up AI systems. Semi-supervised learning, on the other hand, is useful when some labels are available but not enough for full supervision. Self-supervised learning finds the sweet spot between scalability and structure. It combines the massive data utilization of unsupervised learning with the clear objectives of supervised learning. This unique balance allows SSL to deliver powerful, generalizable models that can adapt to a wide range of tasks and domains. Self-supervised learning has transformed natural language processing. Models like BERT and GPT use SSL techniques to learn from massive text corpora, enabling breakthroughs in machine translation, text classification, and question answering. By learning from context and structure, these models achieve remarkable language understanding and generation capabilities. In computer vision, self-supervised learning powers image recognition, object detection, and medical image analysis. By learning from unlabeled images, models can identify patterns and structures that are crucial for tasks like autonomous driving and medical diagnostics. SSL enables AI to see and understand the world with greater accuracy and flexibility. Self-supervised learning is also making waves in speech and audio processing. Applications include speech recognition, speaker identification, music recommendation, and audio event detection. By learning from raw audio data, models can capture subtle patterns and nuances, leading to more accurate and versatile audio AI systems. In healthcare, self-supervised learning is being used for medical image diagnosis, drug discovery, patient monitoring, and medical record analysis. By leveraging vast amounts of unlabeled medical data, SSL helps uncover patterns that can lead to earlier diagnoses, better treatments, and improved patient outcomes. Robotics is another field benefiting from self-supervised learning. Robots use SSL to improve perception, manipulation, and autonomous navigation. By learning from their own experiences and interactions with the environment, robots become more capable of understanding and adapting to new tasks and situations. One popular technical approach in self-supervised learning is contrastive learning. Here, the model learns by comparing similar and dissimilar examples, pulling positive pairs together and pushing negative pairs apart. Techniques like SimCLR, MoCo, and Swave have shown impressive results by leveraging this strategy, enabling models to learn highly discriminative representations from unlabeled data. Generative methods are another key approach in self-supervised learning. These techniques train models to reconstruct original data from corrupted versions, such as denoising or in-painting. Examples include MAE, BEI, and DALL-E. By learning to restore data, the model develops a deep understanding of its structure, which can be transferred to various downstream tasks. Clustering-based approaches in self-supervised learning involve iteratively clustering data and learning representations. The model self-labels and refines its understanding through repeated clustering, as seen in methods like deep cluster and Swave. This process helps the model discover natural groupings and structures within the data, leading to more meaningful and useful representations. The future of self-supervised learning is multimodal. This means learning across different types of data: text, images, audio, and video simultaneously. By aligning and transferring knowledge across modalities, AI can develop unified representations and a more comprehensive understanding of the world. This opens the door to more versatile and intelligent systems. As self-supervised learning evolves, scalability and efficiency are key goals. Researchers are developing methods to handle even larger datasets, train models more efficiently, and reduce computational requirements. By making better use of diverse data sources, SSL will become even more accessible and powerful, driving broader adoption across industries. The next frontier for self-supervised learning is moving beyond pattern recognition to true reasoning and understanding. Future models will develop common sense, causal reasoning abilities, and a deeper comprehension of concepts. This will bring AI closer to human-like intelligence, capable of making sense of complex real-world situations. As self-supervised learning matures, it's becoming more accessible to everyone. Pre-trained models are being shared widely, democratizing AI development and reducing barriers to entry. However, ethical considerations remain crucial, addressing bias in unlabeled datasets, ensuring privacy, and promoting fairness and transparency in model deployment are essential for responsible AI progress. Self-supervised learning marks a fundamental shift toward more human-like AI. By enabling models to learn from raw, unlabeled data, we're moving closer to systems that acquire knowledge through experience and observation. As SSL continues to evolve, it promises to unlock new capabilities and bring us ever closer to the dream of artificial general intelligence. The journey is just beginning, and the best teacher for AI may truly be the data itself.